Welcome. In this discussion, we're going to be looking at chemical reactions. Chemical reactions really kind of builds off of what we've been talking about with atoms and ions and bonding and that sort of business. Essentially, what a chemical reaction is any time we take substances, we break the bonds between them, and then we form new bonds between different things, kind of like what we saw going on with photosynthesis and cellular respiration. As we go through this discussion, which you'll be viewing on Edpuzzle, the video will stop from time to time and you'll be asked to answer a few questions on the screen. Make sure you do. I'm going to be checking to see that you are putting thought into your responses, and if so, you'll be perfectly fine. Also, as we go through this presentation, make sure you look at the screen and the handout you've been provided. Make sure that your notes are filled in and complete, as these will be used in future upcoming assignments. Again, building on what we just said, what is a chemical reaction? It's where we take things, reactants, we break bonds between them, and form new bonds between new things, forming new products. We saw this in cellular respiration when we broke things apart to form glucose. We saw this in photosynthesis when we broke things apart to make glucose. And this also occurs in our body when we take in foods and we break the foods down and we use the small molecules to build proteins, or cellulose, which is a carbohydrate, or nucleic acids, which would be DNA and RNA, or when we use those foods to build lipids, which are fats. Looking at chemical equations for chemical reactions, they are not something we haven't seen, but we haven't talked about them greatly. This happens to be the chemical equation for cellular respiration. We know that because we see glucose going in along with oxygen, and then once again, as going back to what we were talking about with the chemical reactions, we break the bonds between these two molecules, and we form new bonds making new things. In this case, carbon dioxide and water. Again, we spoke of reactants before. Reactants are the things we start with. In this chemical equation, we started with glucose and oxygen. And the products are what are made. We are making carbon dioxide and water. So up to this point, there hasn't been a whole lot of new information. However, moving forward, we're going to be kind of building upon the things that we've talked about previously. Starting with bond energy. Now, think about bond energy as this. If you are holding a pencil, and you're holding it in two hands, can you snap that pencil in half? Probably you can. Now, in order to break that pencil, you have to use your muscle. And when you use muscle, you have to put in an amount of energy. If you don't flex your muscles, you don't use energy, nothing happens, that pencil doesn't break. Well, we can think of these pencils as bonds. A pencil would equal a bond. Bond energy means how much energy do we need to snap that pencil, or bond, in half. However much energy is needed, that is the amount of bond energy required to break it. So the amount of energy that we put in to snap that pencil, or bond, is called activation energy. And if the activation energy is high enough, the bond will break. But if the activation energy is not high enough, the bond will not break. It is important to understand that in some molecules, which all have bonds of one form or another, some bonds are stronger than others, meaning more activation energy is needed to break some, and less activation energy is needed to break other bonds. So not all bonds hold together as strongly as others. You can kind of think about this as like super glue versus Elmer's glue holding two things together. It's going to be easier to rip apart the things that Elmer's glue is holding together and harder for things holding the super glue together. Let's take a look at this graph which illustrates activation energy. This graph shows us time, reaction progress over the course of time, and the amount of energy that's being put into the system. Low energy, high energy. Here we have reactants in a chemical equation. This graph is showing us that As energy increases up to a certain point, the reactants start to be acted on, and when we get to this point, something's going to happen. If we do not reach this point, nothing's going to happen. Think about it like this example off to the right here. We see a guy rolling a ball up a hill. If we want to get this ball over to the side, we have to put an amount of energy in to get that ball up that hill and then down to the other side. If the amount of energy is not put into the moving that ball, the ball stays on this side, the ball does not move to the other side. Same thing would happen with like cellular respiration. If the amount of energy is not put in, glucose and oxygen, they stay glucose and oxygen. They do not become carbon dioxide or water. So we need energy put in to break those bonds. Now there's a couple different things that we should understand about chemical equations. Some chemical equations can release energy to the environment. Others absorb energy into the reaction itself. We're going to be talking first about exothermic reactions. In an exothermic reaction, energy is released. We see the reactants on this side, the products on this side, and the energy needed to break the reactants apart, forming products. In this case, we see energy goes in, but there's less energy over here than there was over here, meaning energy has been lost by these products and energy has been released into the environment. Let's take a look at a video that kind of illustrates this process. So coming back to our slide, what we saw was he was mixing two things together and crunching them and cracking with that spoon, and then he let it sit. Energy was absorbed from the surrounding environment, broke the bonds between those two things, causing, we saw smoke and fire. We saw energy being released in the form of smoke, heat, and fire into the environment. Those things were in here, but they were that energy was in the reactants, but it was released. What was left were the products, which would have been some kind of, burnt, sooty type of thing. That is an exothermic reaction. Energy is released. Another type of reaction is called an endothermic reaction. In this case, energy is absorbed into the products or taken in from the environment. So we have reactants, they have this amount of energy. Energy is put in to break the bonds. As a result, products are made, but energy is being taken in from the environment, and now there's stored energy in the products, meaning there's more energy in the products than there were in the reactants. Let's check out a video on this one.
What I have is some barium hydroxide. Okay, I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk. I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, so I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second. So, I'm going to mix these two things together, and carefully, mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to drink it. Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed a huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you wet yourself, that is the best one you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay. Now, hopefully, if this has worked,
Okay.
it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed.
Oh.
It's actually
Wow.
frozen the water onto the bottom.
That's
Now,
cool.
this reaction has worked so well. So much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom.
How
And
cold?
that is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? Zero. So this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to. But in fact, there's actually ice crystals forming on the side
Can
of the
I
nose.
touch the
Pretty
sides?
cool.
Oh.
Yeah. No.
So again, what we saw in that video was two reactants or solids were mixed together with some energy is going up. To break the bonds between them, we were able to take those two solids, and one of the products that was made, as you heard him say, was water. Well, it was also taking in energy from the environment, which makes the glass that we saw feel very, very cold and actually freeze. So it's kind of the opposite of releasing energy. When we release energy, we're releasing heat, but when we're taking in energy, it feels cold. That would be an endothermic reaction. The last thing that we're going to talk about are called catalysts, or in our bodies, enzymes. Catalysts, what they do is they lower the amount of activation energy needed to turn the reactants into the products. For example, let's think about a reactant being like wood. We want to turn wood into ash. In order to get that wood to turn into ash, we need to apply some friction to the wood. So imagine rubbing sticks together. Say rubbing sticks together, that requires a large amount of energy from you to put into the system to turn the reactants into ash by igniting the wood, by creating the fire. Well, what if we added like gasoline to that? Gasoline would make the wood burn quicker or start on fire faster, meaning less energy would need to be applied to the wood to get the wood to go from wood to ash. All catalysts do is they decrease the amount of energy needed to make the reactants become the products. And in our bodies, these catalysts are called enzymes. So the enzymes in our body are proteins. We'll talk once again more about proteins later on when we start looking at DNA. But there are many different types of proteins. There's a ton of different proteins. Some of these proteins happen to be enzymes. An example of an enzyme is amylase. Amylase is in our saliva. Amylase will lower the activation for breaking apart starch, which is a carbohydrate. It will not act on anything else. That means that the enzyme is specific. Amylase is specific to starch. So picture this. You put a cracker in your mouth and you let it sit. Amylase starts to break apart that cracker, meaning it's breaking apart the bonds that hold the cracker or the starch together. Eventually that cracker will become, mush. Would that happen in water without amylase? Yes, it would, but it would take longer for that cracker to kind of dissolve. Now, if we put a piece of steak in our mouth and we left it there, amylase will be present, but amylase will not break apart that steak. The steak will just stay a piece of steak in your mouth, which is kind of gross. So things that affect how quickly an enzyme can work: pH and temperature and concentration. We'll be talking about those and testing those out in a little bit. So the last thing we need to talk about are the substrates. Here's an enzyme. Here are substrates. We can think of substrates as being reactants. What enzymes do is they take in substrates. They either form bonds, as we see going here, or they break bonds between these substrates. Now, in order for an enzyme to bond to the substrates, we need a lock and key mechanism. That would be called the active site of the enzyme.